Okay, welcome back. So, let me finish up our discussion on convergence of Fourier series. And in particular, last time we had talked about how Fourier series will be pointwise convergent, okay? So essentially that Fs is going to go to the average of the right and left limits if F is piecewise smooth, okay, or piecewise C1 on your interval, okay. We also talked about uniform convergence that will occur if F is C1, okay, then we'll have that the Fourier series is just going to converge to f of x. And I mean, you can essentially see that this follows from this result, because in this case, the left and right limits of f are just going to be, the average of them is just going to be f itself, okay? And then the last thing we noted is that if f is C2, okay, let's say on 0 to L, and let's also take these boundary conditions, right, in order to make this calculation easier. And we showed, okay, that Bn is equal to 2 over L integral from 0 to L of f of x sine of n pi x over L dx, okay? And if we integrate by parts twice, then we end up with minus L squared over n. Well, let me just do pi squared here, right? 2 over L. I'll pull the 1 over n squared out in front. Integral from 0 to L f prime prime of x sine of n pi x over L dx. And we're going to say that this is less than or equal to, or its absolute value is less than or equal to something I'll call m prime prime. So then in other words, the absolute value of Bn, we'll say, is bounded from above by 2L over pi squared, m prime prime, 1 over n squared, okay? And this essentially leads to a bounded infinite sum, okay? And so the problem of function boundedness really gets turned into the issue of being able to bound these infinite sums that define our Fourier series at each particular value of x, right? Because that's what we've done now. We have an infinite series representation. And in this case, the operative theorem is what's called the Weierstrass M test, just because that bound is called an M, called M in this case. So if Fk, let's say, is a sequence of real or complex valued functions, okay, defined, and we'll do this way more general than we need to, on U lives in Rn, okay, and there exists some Mk, okay, such that for any k greater than or equal to 1, and all x living in U, we have that Fk of x is bounded from above by Mk. right? And the sum from k equals 1 up to infinity of mk is bounded. Then, and now this is what we have, our infinite series k equals 1 up to infinity fk. X converges uniformly on U. Okay. All right. So this is our Weierstrass-M-Test theorem, which essentially allows us to use this result in order to say that this infinite series, right? Remember our Fourier series that we introduced in the last couple lectures, right? The sum from n equals 1 up to infinity of bn sine of n pi x over L. This is our infinite series representation for f of x, that is bounded. Okay. Now, one last form of convergence before we move on to other things. Okay. If f is an L2 function, what's L2? It just means that I can take the L2 integral of f of x, okay? Then f of x equals n equals 1 up to infinity bn sine of n pi x over L, okay, is in L2, 0 to L, okay? In other words, for any epsilon greater than 0, there exists some m greater than 0 such that the L2 norm of f minus the sum from n equals 1 up to capital N bn sine of n pi x over L is going to be equal to, right, the square root of the integral from 0 up to L of f of x minus the sum, right, n minus 1 up to n, or sorry, n equals 1 up to n, bn sine of n pi x over L dx, this whole thing squared, excuse me, dx, right, is less than epsilon, okay, for any n greater than or equal to n, okay? Now, that's weaker, but it's easier to prove, okay, as we'll discuss more later, okay? And really, for most applications, L2 convergence, right? This is what's called L2 convergence, okay? Just basically that the L2 norm of f minus your Fourier series, that it tends to 0 as you add more and more terms in your Fourier series. That's good enough, right? Because I know my Fourier series, right? If I take a finite number of terms, it's going to be smooth. It's going to be, you know, about the best smooth approximation I should hope to get for my function. And the only thing I need is a very weak assumption, which is just that f is L2 integral. Okay, so I didn't need continuity, right? I can have weird holes in my function, all those sorts of things, and I get this result. Okay, so so that's L2 integrability. Okay, before I go on, let me say one more thing. Okay, and in particular, you'll notice that I sort of skipped over one specific case, which is what if f is c? Okay, so so just for simplicity, right? Let me take let me take f to be c, let's say, on 0 to L, okay? Well, it turns out there exists an f of x in C 0 to L such that its Fourier series diverges at x0 in 0 to L. Okay, that is in the limit as n goes to infinity, a sum from, let's say, m equals minus n up to n of, let's say, cn e to the in x0. This is going to go to infinity. Okay, so there is a theorem that essentially says that continuity is not enough. Okay, that these coefficients, right, Cn in this case, are the Fourier coefficients. I'm going to say that 1 over 2L integral from 0 up to L of f of x e to the in x in this case. This is just complex exponential version of our Fourier series, me breaking up the sines and cosines and complex exponentials, okay? There's a theorem according to Dubois and Raymard, 1876, that essentially says that we're going to have divergence in this case, okay? A second theorem, okay, according to Carlson, states that if f is continuous, okay, or just Riemann integrable, okay, then this sum n equals minus n up to n, cn e to the I n x is going to go to f of x, right, as n goes to infinity, okay? Basically, for any x on 0 to L, okay, excluding S, where S is a set of measure 0. Okay, what's a set of measure 0? Well, just think of it as a set of points, right? Some finite number of points, right? Or infinite number of points, right? So the definition of S in AB, okay, is a set of measure 0 if for any epsilon greater than 0, S is in the union of j to infinity ij, where ij is some aj to bj, right? And let's say the sum from j equals 1 up to m of bj, I guess this can be from 1 up to infinity, bj minus ij is less than epsilon. Okay, so you can only do that if this is a bunch of points, right? You can basically shrink these regions down to nothing, right, over time. Okay, and this is your measure of our set. Okay, so that kind of helps out with the in-between case. Okay, So C1 is what we need for uniform convergence, okay? C will just cause problems with divergence at particular points, right? And our pointwise convergence is going to apply in the case where C is just piecewise smooth, right? So you could imagine having a situation maybe where the function oscillates a lot, right? So, and maybe maybe you start to have jump discontinuities at certain points as you limit to a particular point here, a particular value of x. And so you don't have continuity, and maybe you even have divergence in your first derivative in that case. So those are the kinds of functions that can lead to this type of pointwise divergence of your Fourier series. Okay. All right. Let me wrap up. I think the rest of this little segment on convergence. Okay. So pointwise and uniform convergence are the strongest, but of course, L2 is the most general and easiest to prove. Okay. We've already kind of shown that our series solution does satisfy our PD in terms of the boundary conditions. Okay. But let's say, let's remember that